record this, so it should have started now. You may have to click on something that agrees for you to continue to participate. But good morning, everyone. My name is Gary Fox. I'm the department head in the Department of Biological and Ag Engineering. I'm also an instructor for E101, section 15. And I am one of the gurus for the river engineering project this year for E101. And let me ask Dr. Lucy Gertot to introduce herself.
So good morning, everyone. So my name is Dr. Lucy Gertot. I am an assistant professor in the Department of Biological and Agricultural Engineering. My research focuses on water resources and ecological engineering. So I look at the processes that are involved in flow and sediment transport, especially in streams and floodplains. And I'm also working on engineering education. So if you are planning to take classes in our department, you will probably have me for 1 or 2 classes at least. Yeah, and so I'm one of the gurus for the River Project.
Thank you. Dr. Castro Bolanaga.
Thank you. So, hello everyone. My name is Celso Castro Linaga. I'm also an assistant professor in the department. Similar to Dr. Gertot, my research focuses on water and sediment transport in streams. And we primarily look into how these two processes interact and shape our streams, and then how that shape basically controls how they adapt to different projects such as stream restoration or the construction of structures or dam removal, among many things. So happy to help with these projects and working with you all.
Very good. Yeah, we're very excited about this project. This is the second year that we've done the project. Last year the previous year was without COVID. So we had the opportunity to actually have you build a design, the teams build a design, and then we actually tested them in our flume. And Dr. Gertot will show you the flume in just a minute. What I thought I would do first is just go over some basic concepts, and primarily just from the river engineering project. So hopefully you can see my screen now. I just shared the project description. And really what we're really aiming at is the fact that we want you to come up with a design basically that's going to replace some of the common structures we use in river restoration and stream restoration practices. River restoration and stream restoration is now basically a $1 billion industry in the United States. Our department has a lot of alumni that work in this area. And in fact, your project that you're working on this year was actually originally proposed by one of our alumni, Chris Bass, who is actually owns Chris Bass Engineering. And appropriate to his name, right, with a bass, we're doing a fish passage study. So, but the pictures that you see in the project description, these are the typical types of structures that are put into streams and rivers. They can be made of rocks. A lot of times people use logs, things like that, really hard structures. So many of these are referred to as what is called a J-hook or a cross vein. In many cases, these structures can actually create a situation that prevents the migration of fish species up or downstream of that structure. These structures are very good in terms of helping us to really control the flow and the sediment transport. A lot of times in stream systems, we like to refer to rivers and streams as living systems. And a lot of times as they go through their evolution and they evolve over time, a lot of times what will happen is if we have an urban area upslope where we're getting a lot of rainfall or just normal rainfall, but we've actually made those surfaces impervious and you're getting runoff into those streams, it can actually start to erode that stream bed, and that bed will actually start to drop down and actually make the banks get steeper, and then the banks will actually collapse in. And then anything on the side of those banks, any types of infrastructure that we might have on the tops will actually start to collapse in. So these types of structures are really put into the bed to try to limit the vertical erosion or the vertical change in that stream bed elevation. But again, these are very hard structures, and in many times they limit the ecology of the system. So a lot of times they're designed based on just hydrology and sediment transport, But in particular, we want to also consider the ecological impacts of the design as part of the river project. So there's a few different things that are going to be part of the requirements for the project. They're listed there under deliverables and then also requirements and constraints. So you are going to design the structure to fit into our existing flume. We do have 2 flumes in the department. Hopefully our second flume will be constructed here very soon. We do have a smaller size flume. Again, Dr. Gerteau is going to show you that in just a minute, but we have certain dimensions associated with that flume. 9 centimeters high, 20 centimeters long, and 7.6 centimeters wide is actually the dimensions of your structure. You also need to have at least one contiguous opening of at least 1.3 centimeters. That could be a 1.3 centimeter diameter hole. It could be a rectangle, something like that, but it needs to be open through your entire structure. Unfortunately, this year, because of COVID-19, what we will do is we are going to actually not have you 3D print these structures like we did in the previous year. We're actually going to have you just send us your 3D models, and then we will use those within a simulation package within Fusion 360, which is called CFD, or Computational Fluid Dynamics. And then we will test your design that way. And again, we'll talk about that more in just a minute. There are several resources that are available for you to use. There's a NRCS Stream Restoration Design Engineering Handbook, which can be a very good resource, and also a USGS resource on fish passage and behavior. That can be a very good resource for the project. When you look at the deliverables, there is something mentioned there that's a research component, and what we really want you there to do is really to look at the peer-reviewed literature, standards, patents, other things that you might be able to find that helps guide your design. If you look down at the actual section on scoring and bonus points, you actually are going to get bonus points if you can design something that mimics the natural habitat of a stream, right? If I'm a fish and I'm trying to swim through your structure, it's very unlikely I'm going to swim through the structure if it looks like it's going to kill me as I'm swimming through the structure. So you need to create a design that mimics that natural habitat, and then the ability for the design to be transferred into practice. And that's really where the research component is going to come across within the scoring rubric. You'll then provide, again, a Fusion 360 model of your structure as well, again, at the end of the project, and we will test that again within the computational fluid dynamics structure. I think with that, that's probably a really good stopping point for me in terms of just a brief introduction. Let me turn it over to Dr. Gerteau, who's going to show you some videos and some other things that you can use to kind of get an even better feel for the project.
All right, so let me share my screen. So what you see here is the same flume as we have in Weaver Labs. And so if we get closer, you can see what happens if we have just a flow that is not disturbed by any type of structure here. So the water level is almost the same everywhere. And then you will see what happens when we place actually a structure in the stream. So this is called a broad crested weir. And so that can represent the type of structures we put in the stream, such as the G-hook. And so basically what it does is it creates an obstruction in the stream. So the water here is flowing from the right to the left. So the water level on the right will increase. And then on the left, you will see that the water level will basically be less higher. And the velocity or the speed of the water will also be higher as well. So basically it changes how the volume of water is distributed upstream, so on the right, and downstream on the left of the structure. And that causes also an obstruction for the fish. So it's a solid obstacle, so the fish is not able to pass through that. And on top of that, the conditions on the left are not really suitable for the fish because the water levels are too low and the velocity or the speed of the water is too high. So it's not a good condition for the fish to be able to swim there. So think of it as like the worst case scenario that a structure can do in the stream. And so what we want you to do as part of the project is really to try to create a structure that is different from this one and will improve the conditions. So having a higher water level or water depth on the downstream and try to lower as well the water level on the upstream part and having some openings or hole in there or some kind of way the fish can swim from the downstream to the upstream, so against the flow. And so let's see. So you can see how fast the flow here is, and that's not a good condition for the fish. So what I can do now, oops, is show you some examples of designs that we used, that students have created last year, and discuss what they are doing and whether they were good examples or not very good examples. So here, for example, you see that it's a huge block, and I think it had openings in here, something like stairs. And it didn't fit quite well into our flume. So you see here at the bottom, there is some space. So make sure that the dimensions of your structure fit really well the specifications. So you can see here the water level upstream on the left is quite high, and downstream on the right, it's quite low and very fast. So overall, this was not like a very good solution. It did not provide adequate conditions for the fish to be able to pass through. Of course, it's open, so they could pass through, but in terms of water depths and speed, it's probably not very suitable for the fish. So I can show you other examples. This one as well, I think, was a solid weir with holes in it, like openings at different levels. And so similarly, it does not really improve the conditions compared to the huge wooden block that we saw. So the broad-crested weir that we saw in the previous video. The water level is still really high here and quite low, and the flow is fast on the right as well. And so let me see if I can show you one more. So here you see an example of another structure which was a bit more innovative with different types of holes in here. So you can see that it provides like more room for the fish to pass through, but it's still not like ideal because the flow here is still very fast. So our goal is really to be able to increase the water depth, so the amount of water that is able to pass through the structure, to make sure that we even out the volume of water on the left and on the right of the structure. And with that, I think Dr. Castro Bolinaga has other examples of pictures to show you.
Yes. All right. Thank you, Dr. Corto. So let me go ahead and share my screen. And first, before showing you more examples, I'm going to show you basically where this project was originally inspired, as Dr. Fox was mentioned in the beginning, for one of the stream senior design projects. Here you can see This is a fish ladder built around the dam. These type of structures are very common in the northwest part of the United States. And you can see basically the inspiration for some of the structures that we saw during the only time that we have actually done this project. And you see the obstructions around the ladder. And basically the idea is that you will create fast moving areas of water and slow moving areas of water so that fish can actually go through upstream. And here on the bottom, you see some fish patched structures as well, but these ones are more intended to mimic the natural environment. So you see a lot of rocks. The idea is the same. Rather than having these type of steps in the dam, you have rocks that basically create areas of high speed and then areas of slow speed so that the fish can actually rest as it moves upstream. And then the project that they actually did was basically with these tetrapods. The design from the senior design team was basically interlock all of these tetrapods, and so the porosity created by the structure was going to allow the same principle, areas of slow and fast moving water so that the fish can go through. And I actually have a sketch of the design that they have, and it will look basically something like this once it is installed. And the inspiration for this project was a dam in the Dam River, close to the border between Virginia and North Carolina. This was going to be as part of the dam so that the dam can basically can be relicensed and then allow for endangered species to go upstream. So now let me show you some of other examples. So here I'm going to show you four. This one right here, this green structure is the very first one that we tested. It basically had, I think, about the half of the height of the block. And then you see some V-shaped type of structures basically located in the middle. And if I click play, you will see that it has basically the same flow patterns, very relatively deep waters upstream, and then the flow gets shallower and faster. And then you have faster and shallow flows going into the downstream direction. So in terms of how much it changed, it reduced the amount of water upstream and increased the one downstream, but it didn't have a large effect of some of the others that you will see. This group took the concept of a fish ladder on a more literal interpretation. You can see that it is actually a ladder for the fish to climb to the other side. In contrast with the previous one, you see that the water depth upstream is significantly higher, so to your left. And then you have basically a waterfall where the water accelerates and then goes downstream. This structure has some holes in the middle, and I think that was the idea that this group has, that the fish can actually go through the holes that you cannot see here. This one is more like the one I show you for the dam structure. So it's a labyrinth type of structure, where in theory the fish can go in and then swim across this structure where the flow velocities are going to be much lower than what you have outside. You see the same pattern. Upstream is relatively deep, and then flow accelerates and travel in the downstream direction. And then the final one that I'm going to show you today, they had a little bit of a fitting problem. You see a gap between the bottom of the flume and the bottom of the structure. So this in theory should not happen. And they have literally maybe 10 to 12 holes in the middle of the structures, and then water was just flowing through these structures. And actually you can see water going out of the top ones, and the lower ones are actually submerged. So same principle. They are trying to generate flows of fast and slow moving water. One question that we have received in the past doing this session is how, since you're not testing the structure, how can you actually have a proxy to understand how well your structure will perform? And we have said that volume occupied can be one. So you have a structure that will take one volume, that is basically the worst case scenario. And then your structure should reduce that volume that is occupied by that block. So you can actually make an estimation of that based on the porosity of your design, or how much free space do you have.
Okay, very good. Hopefully you can tell that we're very passionate about this topic. This is something that we work on, and we do a lot of work on as a group within our department, and something that I think is going to become even more important moving forward as we put designs into stream systems, and we want to try to do these in the most natural way possible that we can. So I think what I'm going to do now is I'm actually going to stop the recording, since that's the kind of the overview part, and then we'll open it for questions if anybody has questions.